again and welcome to another video. Today we'll be combining the knowledge we've acquired in the videos C++ optimizing move and destructor semantics, C++ hacking destructor semantics part 1 and part 2, and C++ static storage implementation, as well as recursion into Goto Labels, including the entire series. So last time in the recursion being turned into Goto Labels, we had left some unfinished business and we have left important optimizations behind in order to really start using the recursion translation that we've made and applied. So to take a step back, what I mean by it is we have the call frame here and we move it into the stack via move, but before that we are forced to call or prefill all the constructors of the call frame, but that's not going to happen on each of these calls because we are using a static call frame. However, we have to avoid using call frame as this, and we should use something like this. Make sure to check out the video named C++ static storage implementation in order to understand why we are using static storage here implementation. And if we go to the definition of this, we can see that we are trying to lazy allocate buffer on stack as opposed to having to rely on pre-filling all of the entries before we get to use the buffer. And C++ has to make sure to do this because we don't want our code to result into undefined behavior. But in order to prevent that, you would use something on you would use unsigned character on stack and go from there. So first our theory was to, and our practice here as well, was to have each call frame and push it before we make the actual call. And this translation is derived and created from the typical recursive function that we would write. And to be honest, the easiest way to translate something like this is to look at an assembly. Like I said, when you look at expression at face value like this, it's difficult to figure out what are we trying to do. And if you break it down into variables, now we are seeing where we are going to return from a function and what we are going to do with that value afterwards, or from that point on. And that can be extremely helpful once you're determining the origin of your call, once you jump to your computer go to as part of your call frame. So the first thing that I really don't like here, and it's probably the first optimization that we would make, is we have the shared PTR here and we are applying a copying here because we are referring to it as L value. So within our call frame, we will be unnecessarily so invoking the copy assignment of the share pointer, and the share pointer implementation is really complicated and contains a lot of ifs and else's. So if we can find a way to figure out how not to make that copy assignment, then we will straight away get a head start in performance, no questions asked. Because on a copy assignment of the share pointer, under the hood you would have a lot of conditional jumps in your assembly, which is not optimal and it is not feasible at the end if you're trying to benefit from a translation, from such a translation from the recursion into the Goto labels. So now, because we are 100% sure that we are passing this value as constant reference, we can take a pointer of the shared PTR, and because a pointer is also going to be like 8 bytes, and we are not going to invoke the copy assignment on the shared pointer, including all the conditional jumps under the hood or behind the scenes, we are going to get an enormous boost up, which I'm gonna break down in a moment. So now if I look at my struct of the call frame, I have the pointer of share PTR, and it has to be a constant pointer because we are using a constant reference. And this works because pointers in C, C++, once they're defined in const, they're const in terms of not the variable, in terms of the value. So if you want to have an immutable, so your pointer in this case is still mutable. If you want it not to be immutable, or rather immutable, you would do something like this in C++. So yeah, and now that we've made that optimization, we are just referencing it here by a pointer, picking it up, dereferencing it when we need to use it, and that is that. So that's where we're gonna get huge performance boost right off the bat. Now the next performance boost is to use the call frame, to use the static storage in the call frame. Now, because we're using static call frame here, we are still going to hit similar performance because it's static. It's a global variable after all. It's not gonna run expensively in our benchmarks at all. But if we do something like this, then we are running in a lot of trouble, and it's really slow. See, we are hitting 0.017 sometimes this. Well, in the end, it's not that bad, but still we are not gonna hit something like this, which was a really huge overhead, 25 and 49. So even though we are not going to make a lot of a difference there, I would prefer to use static storage all day, every day, especially if I'm having other translations in my code where I'm not required, or I cannot depend on the globally defined static variable. So now if we look at this translation line by line, our push in the static storage is just going to be our macro. Make sure to check out the video C++ static storage implementation to get up to speed with what I'm talking about here. And then we have the function arguments. That's going to be pretty much the same as this, is that we have the last, we take the last, this is essentially just the last element of the stack, and then we dereference it. Same for this, is the last element, and this. And once we are assigning the node onto our call frame, we are picking up the pointer. And you would use pointer like this always when it comes to situations like this, like having to pass around constant reference from your or within your recursive function. And that's because first you're saving up space, and second you're not enforcing or applying additional operations such as copy assignment that behind the scenes contain actually a lot of overhead, and as a result it's a pain in the neck when it comes to the performance, and we are not going to get a significant boost up that we would expect otherwise. So then we have the push, which is essentially this. Now, one thing about this is in the video named C++ Optimizing Move and Destructor Semantics, we talk about how we are enforcing another move here. And I wouldn't prefer to enforce a new move, because I'm 100% sure I'm moving this out of my scope into another piece of memory or another entity, such as call frame static storage or stack. And plus, at the end of this call, if my compiler is not using optimizations at O0 level or O3 level, or actually if my compiler is not using optimizations at O1, O2 and O3 levels, this is going to result into call frame destructuring, where the structure is going to be invocated at the end of that expression, or in other words where the semicolon is of that expression, because semicolons represent where the expressions end in general. And then I'm gonna enforce call frame, and that would be the move constructor. Call frame. So I would enforce the two. So in order to avoid this, and like I said, we talk about this in the video Optimizing Move and Destructor Semantics on this channel, you would write an inline function that would make your entity or your object, where I'm gonna say where we can enforce copy elision. So now we have call one. I would take all these and figure out what do I need to pass in as parameters to move them. In order to sort of to apply our dark magic or go nuclear when it comes to performance improvements. So I would pass in shared, it's going to be const shared PTR 3 node, and now it's going to be the left node, and then we have call origin, call one origin, which I believe, since it is a computed goto, we would use the void pointer. and then you have call1 origin, and your left will be here. I would also just, so I'm not paranoid about whether or not my call was inlined, I usually do always attribute always inline, which is supported both in Clang and GCC. So now once I do my push here, I'm going to do storage push stack make call1, and then I'm passing on my node, which is going to be node.get left, and then I'm gonna pass on my call1 origin, and that should do the trick. Let me just oh yeah, we also need the type specifier, which we also cover in the video I talk about. I should be I'm too accustomed to using the S class in my videos that I sometimes forget. So it's gonna be call frame. Oh, I'm also not allowed to include attributes in the function definition, so we will have to go with this. I believe in C you can do that, maybe. So yeah, that will work. I just have a terminal on my other screen to compile this stuff and check for any errors at compile time. So that will work. That's how you would avoid the unnecessary or the redundant call frame and call frame move constructor, which will be enforced since storage push does the new placement here, and the new placement would convert into a move constructor. So now if we move on, we can, if we proceed with our line by line comparisons, we can see that this is pretty straightforward. This says last item of the stack, and now stuff really gets interested here when we need to reference what we returned from our call origin. And for that reason, I implemented in the static storage at, and then I would take this stack.stack count, since at that point would be, let's say, the length of my stack, or the stack, or the item count is 1, it's going to be 2 in this case, because at the return point of our translation, when we are jumping to the computed goto, which is an indirect jump in assembly, we are referencing it as something we popped off the stack. So in order to get to our computed goto, we're not going to access the last element, we're going to access the stack count, since we already popped that element. So it's not going to be -1, it's just going to be the count. Or you can create a temporary variable here that says, I don't know, this was my current last index item, and you're going to say stack.stack count -1, and then you can proceed to do the pop and then use this one in here. So that's essentially what the translation is going to look like. And now let's get to benchmarking. So I will take the first, my benchmark looks like something like this. I take the size of, and this is, I believe, 10,000. And then when I'm benchmarking, I'm just creating a root that is going to sum my binary tree, and then I'm gonna measure the performance of this expensive loop. Okay, so now I can see that I'm having 004, and with my unoptimized recursion translation I'm having 001, and that is, and I'm gonna get 007, but this is twice as fast. So now let's break down the performance stats using the Linux perf tool. So the stat that I'm looking at here is the CPU core instruction. I'll take this. So we are at this point executing 12 million CPU instructions. And let me just compare the two. And here I have 19 million. So we are about 7.5 or 700 million core CPU instructions faster. But this is not the worst case scenario, by the way. The worst case scenario for our unoptimized loop, and it happens quite often, as you can see. 18, 29 billion, 25 million, actually 35, 29 million. So it is, we can say it happens more often than not. And on average, I mean, in that case, at the worst case scenario, we are about 21 million CPU core instructions faster, which is through the roof, just through the roof. And if I try to get my worst case scenario for CPU core instruction for my optimized recursion, I will never reach 20 million instructions. It's just 26 sometimes million, but that's really rare. Alright, that would be all for this video. Thanks so much for watching, and make sure to subscribe to the channel. Take care.